Hello everybody, we will continue our lecture series. Last lecture we have seen the generic theory of this model predictive static programming MPSP, and we also saw this some of these applications in the reusable launch vehicle and things like that, re-entry guidance of reusable launch vehicle, things like that. Here what we are doing here is actually, as I told in the last class, we will take you through some sort of missile guidance problems, and I will take you through a number of, essentially different class of missile guidance problem. I can see the generality of the and applicability of this particular method that I am talking about actually. All these are practical problems, and these are not just benchmark examples or things like that actually. Okay, so, we will see that one by one. So, outline of this particular lecture is some little bit philosophy of or principle of missile guidance. And then I will talk about optimal missile guidance using MPSP, where ballistic missile guidance as well as tactical missile guidance I will talk with impact angle constraint. And also let me also repeat here, this what I am talking here is more of theoretical nature. If you want to implement any of these in the real vehicle and all, you have to do many other things which is obviously not part of this lecture and all that actually. Okay, so don't think that you can just take it and then directly implement in your vehicle and all that. There will be several other other things that you need to verify and verify rigorously rather before implementing anything like this actually. But having said that, you can see the applicability of this particular method in two different class of problems actually under the simplified assumptions that I am talking about there. So, first thing is what is the strategic missile guidance? This is essentially this ballistic missile guidance and all that what you talk about. It essentially is some vehicle takes off, lifts off, okay, from here, and then after some distance, some height covered really, your dynamic pressure goes down, and that is where your you can think of maneuvering your vehicle rather easily actually. So, then there is something called guidance loop closure. So, from there onwards the vehicle is actually guided. Up to that is some sort of a pre-programmed maneuver. It is not really vertical, but pre-programmed maneuver, little bit turning sort of thing, which will go to in the direction of target, but not really very close to that. But essentially it will also make sure that the vehicle is safe actually. So, within that is the first part of pitch programming and all that, and after that there is a guidance loop closure, and here onwards the vehicle needs to be turned actually. Okay. So, this is what will happen, the vehicle will keep on turning. Okay. Then there will be some sort of either a thrust cutoff or there is a burnout thing. Okay. That means, if you go with the solid motor propelled vehicle, then you have to wait until it burns out, or if it is a liquid engine propulsion actually, then you can think of cutting off the thrust anytime you want actually. Okay. So, the guidance phase starts somewhere here and ends somewhere here, and at this point what it should happen is your height, ultimately the location, as well as the velocity magnitude and its direction, that is this flight path angle gamma, should satisfy a particular condition. So, that for further onwards it actually goes through some sort of a free flight, and this free flight will be target intersecting actually. Okay. This is what you are talking about, is a strategic target sort of thing on the surface of earth. So, essentially it will go to in the free flight mode, and what you are looking for is that particular trajectory which will essentially fall on the desired target actually. That is what your is very fundamental or basic philosophy, things like that actually. Okay. Also, you can somewhat very cleverly you can see that essentially this problem is can be extended to launch vehicle guidance as well, because what you are looking for is you are looking for some sort of a trajectory, okay, some sort of a condition with a lot more velocity, okay, so that it will go and actually it will come like that. Okay, that means your earth curvature is like that, but the trajectory is not intersecting the earth actually. Okay, that means it will go round and round, and then it essentially leads to this satellite orbit sort of thing actually. Okay. So, this particular method what I am talking here is relevant to both ballistic missile guidance or strategic missile guidance, as well as this launch vehicle guidance, ascent phase guidance actually in general. Okay. All right. Okay. So, also remember that the condition has to be such has to be such that ultimately you will be able to cover this range angle actually. Essentially, this is phi t, the target range angle from starting from burnout actually, that way. That becomes an additional constraint actually here that way. Alright, so this is what the problem is, philosophy is. Okay. And okay, before I forget, remember all the corrections that needs to be done is here, and this happens to be, even though the picture is amplified a little bit for clarity, this happens to be a very small segment of the trajectory, for about something like 5-10% of the trajectory. So, for rest of the trajectory, for about 85-90% of the trajectory happens to be just free flight actually. Okay. And so, in other words, you are actually trying to kind of throw a bullet out here and throw a stone or bullet, whatever you can think about, so that the stone, after throwing, you don't have any control, but you have thrown it in such a way that it will go in this free flight and then intersect the target actually. That's the problem here. What about the tactical missile guidance? See, you have got a target which is not stationary, which is kind of intelligent actually. So, target keeps on moving and you are a chasing vehicle. So, you try to kind of chase this vehicle. Okay, okay, let me, this is the missile that we are talking about, the target that we are talking about. Okay. The target has its velocity Vt and missile has its velocity Vm actually. Okay. And there are a couple of terminologies out here. Okay, this line joining the missile and target is essentially something called line of sight. And then from the horizontal reference line, if you draw some angle, I mean this LOS will make some angle, that angle is nothing but LOS angle sort of thing. And then this wait, okay, that's the LOS angle. And with respect to the LOS angle, the velocity vector of the missile will make some angle theta m actually, and the target will make some angle theta t. Okay. So, remember again that this Vt, the target is going, it is capable of maneuvering and all that actually. So, it can also change its velocity vector direction that way. So, what way you can assure that this Vm is essentially guided towards that, essentially it should go and hit the target that way. So, the one idea here is you have this lateral acceleration generation mechanism through the lift vector. So, remember the drag is along velocity vector, okay, opposing that, and the lift is perpendicular to that. So, we can think about lift by mass, which is essentially some sort of acceleration quantity, and that is called as lateral acceleration actually. So, the idea here is if you generate some sort of a lift, additional lift and all that, in whatever direction, positive or negative either way actually, then we are essentially able to change the velocity vector direction. That is more important actually. So, once you change it, essentially it will happen in such a way that ultimately you will change a little bit here. So, that if the velocity vector goes of the target goes that way, the velocity vector of the missile will be aligned somewhere like that, okay, and then it will both will ultimately go towards some sort of a collision point actually. Okay. And if you little bit closely looking, what it turns out that after some time the LOS vector, what you are looking as this LOS line, the LOS vector remains parallel actually. Okay, that means there is no change in the rotation, I mean there is no rotation of the LOS vector really actually. So, that is that's what it is, the very fundamental philosophy. So, in other words, you have to do something so that this LOS vector should not rotate. That is the whole philosophy of classical missile guidance actually. Okay, so there is a very popular missile guidance law which is called proportional navigation guidance, which essentially tells you that okay, you generate this AM, that is your essentially the control variable in the guidance law this way. That means n times Vm into lambda dot, lambda is this and then there is a rate of change of lambda. Ultimately, you do not want any rate of change actually, you know that. Okay. So, guidance law happens to be something like this. You generate a lift vector and this is a time varying value, remember that. So, you generate Am in the as per this formula n Vm lambda dot. Vm is already known to you from your own sensor. Okay. Lambda dot is again sensed through its own inertial navigation system and things like that, as well as the target tracking mechanism. That means either using radar or seeker either way actually. Okay. Typically, these are end games, so you use seekers actually, which will in other words you will directly see the target from using your own instrument actually. Okay. So, anyway, so this lambda dot and Vm is the only thing that you need to evaluate. Okay. And then once you do that, n is just a constant number. Okay. So, that your typically value is something like 3, 4 and maximum 5 probably like that actually. Ideally around 3. Okay. There is a reason for that, we have discussed that in one of the previous lectures as well actually. Okay. Anyway, so coming back to that, this is your AM, typically generated that way, and it happens to be kind of an optimal guidance law in a restrictive assumption sense, and all those things we have discussed before already actually. There are several conditions. If it meets those conditions, this is nothing but an optimal guidance law, provided n is selected as 3 actually. So, that is the reason why n is hanging around the 3 value basically. Anyway, so I will not repeat those. Let us move on actually. So, this is a very simple guidance law. It has been used in many missiles and all that actually. It still continues to be used, and there are many versions around that as well. Something like true proportional navigation guidance, that is called TPN. Then there is something called PPN, pure proportional navigation guidance. There is something called augmented proportional navigation guidance, and so something called modified PN, and things like that. There are various versions of that actually. But all these can be clubbed into this classical missile guidance ideas actually. Okay, so this is ultimately what it happens in the technical missile guidance sense. And remember, this picture is in 2D, and ultimately everything in aerospace happens in 3D. So, there are extensions for 3D as well actually. Okay, you have to apply this lift vector in 2 different directions actually, and it is possible because as a missile you can think of generating lift in 2 perpendicular directions, which are both perpendicular to the VM direction. Okay. Perpendicular to VM is a plane, and in that plane you construct these 2 different lines orthogonal to each other, and then try to generate in 2 different directions actually. That is how you take care of these 3D problems actually. Anyways, these are the fundamental philosophy of missile guidance, both strategic as well as practical actually. And to summarize, many missile guidance laws are actually inspired from observing nature. That is, as I told, the proportional navigation guidance law is based on ensuring this collision triangle. I mean, this is what you saw here is essentially what is called as collision triangle basically. Okay. We have to assure that the collision triangle is satisfied actually. Okay. And there are control theoretic guidance laws also available. That means you pose some sort of a relative kinematics and all maybe in a little bit point mass dynamic sense and nothing like that, linearized point mass dynamics or something like that. And then there are control theory things available, which essentially tells you that somehow I know that this line of sight rate should be 0. So, what should I do? What feedback clock should I use so that the line of sight rate remains 0 actually. Okay. So, these kind of ideas have been explored, but they typically use this linearized dynamics actually, okay, because using that you can get a closed form solution and then proceed further for analysis and synthesis basically. However, remember neither linearization nor this observing nature is actually a very natural way of doing things, or very rigorous mathematical way of doing things rather. So, what it happens is the system dynamics turns out to be typically nonlinear, and hence nonlinear optimal control theory is somewhat, in my view, a natural tool for obtaining effective missile guidance laws actually. Okay. So, let us see how to do that, but then as I told, if you once you have a nonlinear optimal control formulation, then it typically gets into these computational issues. However, because of the recent developments like that, like MPSP and other things, it is possible to use some of these actually. Okay. By the way, all this MPSP, this I mean adaptive critics, the SNAC, and then this SDRE theta D, and then all this. I will also talk a little bit about model practice. I mean model practice static programming MPSP is what I am talking about, and then pseudospectral method, and also this model predictive control process. All these things are actually developing towards this online application sort of thing actually. Okay. Anyway, so these are the things. So, essentially what I am telling you is this nonlinear optimal control theory is a natural tool to obtain effective missile guidance laws actually. But the problem here is how to address this computational issue, and as we saw in the last lecture, MPSP happens to be one of the candidates which essentially guarantees you computational efficiency as well as guarantees you terminal conditions being met as a hard constraint, which is more important in missile guidance actually. Alright, so this is when you do that, attempt to do that, first you need to have some sort of a relative kinematics or relative dynamics between them, and this is what will happen. Okay, point mass missile model with flat and non-rotating earth if you take, it is very easy to analyze that x dot happens to be v sin, if this is x and this is y, let us say, and this happens x dot is nothing but v cosine gamma, and h dot height dot is nothing but v sin gamma. These two are very easy to see, but these two, if you this v dot and gamma dot, if you see that, okay, Essentially, this is nothing but force balance in the direction of V and perpendicular to V. So, mv dot is essentially the total force acting along the V direction. That means, mv dot is nothing but the force component coming out of the thrust, which is T cosine alpha, minus the drag acting on that, and minus the gravity component mg sin gamma. Mg sin gamma will act on this particular this mg happens to be like that. So, mg sin gamma is some component here in this direction actually, which will also oppose to the mv dot component. So, mv dot is T cos alpha minus D minus mg sin gamma, and hence v dot is nothing but 1 by m of all that actually. Similarly, if you see the force balance, net force acting on the perpendicular to the velocity, that means the lift direction, then essentially it is T sin alpha, okay, T sin alpha plus lift itself minus mg cosine gamma, okay, this direction actually. Okay, so this thing if you divide it by, if you see that is nothing but mb gamma dot happens in that direction. You can, typically you can think about this this gamma dot acting on that, and there is mb and then things like that actually. Okay. That means it is like a centrifugal force sort of thing actually. You can see that way. So, gamma dot is nothing but 1 by mb into this quantity. So, if you just take a 2D problem and then you assume that it is a flat earth and non-rotating earth and all that, these are the system dynamics that is necessary. First two is represents the position coordinate, and these two represents the velocity component, dynamic variables. And again, if you go to the 3D sense, then what you need is y dot also here, and what you need is psi dot also here. Okay, psi dot, or sometimes people call it chi dot actually. So, V, gamma and chi together, and x, y and h together will define the position actually. X, y and h together will define the position. V, gamma and chi will define the velocity vector completely actually. So, what you, if you just take 2D problem, then these two are kind of not needed. 4 equations are good enough actually. Okay. And also remember this D and L will contain the alpha terms actually. So, what you see simply as cosine alpha and sin alpha here, they don't appear just like that way. D is essentially a function of CD, and CD is a function of alpha actually. Similarly, L is a function of CL, and CL is a function of alpha. So, this happens, what happens in pitch plane maneuver sort of thing in 2D. But if you talk 3D, then this sigma also has to be taken into account, velocity vector, the vehicle roll and things like that has to be taken into account actually, and then alpha and sigma will act together as some sort of guidance parameters actually that way. Alright, then point mass missile model with spherical and non, this is what happens in flat earth sense, flat and non-rotating earth. Okay. What happens in spherical and non-rotating earth, that is what we are going more and more towards reality, but how much reality you want to cater for depends on the particular mission actually. In other words, if your vehicle happens to be in the range of 20-30 kilometers, you really don't bother about this the spherical nature of the earth and all that. But if the target range happens to be quite far away, like let us say 1000 kilometer, 2000 kilometer like that, then you have to account for the curvature of the earth actually. So, essentially it will lead to spherical earth. Now, whether you want to have rotating or non-rotating effect, again that depends on your time of flight and your latitude of launch point and target point, latitude difference between launch point and target point actually. So, that is again the point here is you take that much complexity what is required for the problem actually. But nevertheless, it is possible to handle various degrees of complexity actually. So, the point mass missile model with the spherical and non-rotating earth, typically what we use in strategic missile guidance and all that is something like this. So, you don't no more talk about x dot and h dot and all that, but r dot is kind of h dot, r is nothing but radius of earth plus height. So, r dot is h dot actually. So, this is V sin gamma, and then this theta dot is now the reference angle just from for a particular reference line actually. So, this theta dot you can think about this, maybe this point is your launch point, okay. Then joining that to center of earth, you will define the reference line, and then with respect to that reference line, you can talk about an angle theta with respect to the current position of the vehicle. If you join to the center of earth, the angle between the two is nothing but theta, and that theta dot, rate of change of that angle depends on the tangential component of the velocity vector, which is nothing but v cos gamma. Okay, v cos gamma happens to be like that. You can think about okay, what is happening here in this picture is this is nothing but the surface of earth, okay, the radius of the circle V, and circle A is parallel to surface of earth, okay, but happening at the current location of the vehicle actually. Okay, that is where all the dynamics happens like that, that way. But remember this velocity vector can be anywhere. Okay. So, this velocity vector is not tangential to the circle. Okay. So, what you are telling here is, let us imagine one more circle here, okay, which will, for which the velocity vector is tangential actually. Okay. And then it turns out that, okay, if you join it, the center of this particular circle, you can think about something like here, and this the radius R, big capital R, and this is the radius small r and all that actually. Okay. And this happens to be this RE, the radius of earth basically. Okay. So, all this little bit force balance analysis, if you do it properly, then all that you will end up with this set of equation. Let me not go through the derivation part of it, but I think if you just look a little bit carefully, what is mv dot for example, okay, mv dot is all the forces acting along that direction. Again, it is the component, say here the guidance parameter is the thrust deflection angle, let us say. That means, how much the thrust is reflected from velocity vector direction. It do not get eluded by this alpha, is not really aerodynamic angle of attack per se. Okay. But if you think the vehicle is still under atmosphere and then the thrust is along the body of the body x axis of the vehicle, which is typically true, then this alpha happens to be angle of attack as well actually. But if it is extra atmosphere mission, then there is nothing called angle of attack actually. Okay. So, think about that, this alpha being something like thrust deflection angle with respect to velocity vector. So, that is that's what it is. So, T cosine alpha minus T minus mg sin gamma again. So, that part happens to be like that, but gamma dot we will have a little more complex. See, earlier it was only this much, now this additional term will come because some sort of a centrifugal force. You can think about this force, what you are looking here is like a centrifugal force with respect to this particular circle basically. Okay. And mv gamma dot happens to be in that particular direction actually. Okay. More on that, you can see some textbooks on this dynamic equation derivations, all that actually. Okay. Now, coming to the first problem, we will talk about ballistic missile guidance with solid motor especially. Ballistic missile, when I talk, is that these are strategic vehicles and all. And again I emphasize here, these are all theoretical studies. I mean, lot of things are actually now nowhere close to practical things, but essentially we have taken as much realistic things as possible to experiment in an academic environment. So, that the conceptual things can be kind of verified actually. What you are aiming here is verification of the technique rather than going for a particular mission and trying to kind of mechanize everything around that actually. Okay. Alright, so just a little bit of motivation why you want to have solid motors. First of all, this class of vehicles, what is strategic vehicles, are typically meant for deterrence actually. That means these are not kind of attacking vehicles and all, but if some enemy already attacks us in a way, then there is no choice, you have to retaliate back and things like that. So, that means the reaction time happens to be small actually. So, that means you really want quick firing. And quick firing is possible only with solid motors, not in liquid engines, because when you have liquid engine propelled vehicles, it requires a lot of preparation times and all that actually. Okay, why for and all, there are different reasons for that. The liquid, the fuel tanks has to be pressurized well, and it has to be, it cannot be done, it cannot be kept like that for a long time. The liquid has to be pumped in as and when it is required, because it is also corrosive liquid and all that. So, there are reasons for that actually, why it cannot be done. Okay. But here it is possible, because once you have a solid motor, you just have a casing and then just maintain it to keep on doing that actually. Whereas when it is needed, you can simply start firing it actually. So, with very minimal preparation, you can go for the mission actually. And there are reasons for, there are other reasons as well. Essentially, if you see solid motors, there is nothing called sloshing, because there is no liquid actually. So, sloshing problem is simply not there. And there is nothing called tail wags dog effect also. Okay, TWD stands for tail wags dog. Typically dog wags tail, but there is a concept in aerospace which talks about tail wags dog actually. That means, if you talk about liquid engines, there is a kind of engine swiveling concept actually. That means the entire engine is kind of swiveled using these motors and all. And this is also a dynamic correction. It is just not one side correction and stop actually. It keep on changing left and right like that way. So, when the frequency of this oscillation happens to be close to the natural frequency of the vehicle goes through this violent oscillation and all. Essentially, there is a mission failure actually. So, those things are not here in solid motors, because essentially there is no engine. So, in the engine swiveling mechanism is not there actually. So, what is there is essentially this nozzle deflection ideas and all. So, for that you do not require that kind of heavy moments and all that. So, it is typically not there actually. Okay. The cost part I will not I mean I will not like to go into that, but typically it turns out that essentially solid motor vehicles happens to be slightly cheaper actually. Okay. What is the advantage? So, what are the penalties actually? Okay. So, penalty is there is absolutely no thrust cutoff facility. I mean, there are limited attempts people have done and all that. That's a different story. They have some plugs and they take out, the chamber pressure drops and then the fire gets extinguished. But we don't want to talk about that. In general, what happens is there is no thrust cutoff facility. Once you fire, it has to exhaust its energy, whatever is there, and then it has to I mean do the mission actually. So, you don't have this luxury of cutting off the thrust as and when you wish actually. Okay. Then there is this issue of burn out time being uncertain, and there is an issue of non-manipulative thrust time curve also. If the thrust time magnitude cannot be increased or decreased. So, on the other hand, liquid engine is like some sort of a car engine actually. If you want more power or more thrust, you burn more actually. That kind of thing can be done here. But here it cannot be. Whatever is stipulated or whatever is pre-selected thrust time curve, around that it will operate. And also remember, thrust time curve, whatever is specified, then it is not going to happen exactly like that. There will be variations around that actually. And part of that will be kind of known variation, and part of that is uncertain. They are typically not known actually that way. Nevertheless, it has to happen. Your guidance must end at the burnout point, and that should satisfy the target intersecting trajectory and all that actually. So, essentially the guidance part becomes quite difficult here. Now, system dynamics, these are the variables what you are looking here, and then alpha I redefine as something like a shear angle guidance, guidance parameter delta sort of thing, and using that this system dynamics is rewritten something like this, neglecting the earth rotation actually. Earth curvature is taken into account, but earth rotation is not actually. Yeah. So, these are the system dynamics. Okay. Then there is some concept, this going back to the same picture. The beauty part is this pre-flight equation is kind of known if you take about a non-rotating spherical earth. Okay. And this part of the trajectory is actually given by this sort of equation. This is all derived in 1950s and all that actually. Yeah. This is the equation which will govern this part of the trajectory. Now, what happens is, okay, this is the current, this is the any point of time, this is r, and this is my angle theta basically, what you see here. So, if I really think about my this target hitting sort of ideas, target intercepting sort of ideas, this equation, from this equation you can derive the so called this heat equation and all that. What it turns out is you just substitute r as RT, okay, and then substitute this theta as something like phi BO actually. Okay, phi BO is nothing but this phi t minus phi 0 sort of thing. Okay. This phi burnout, okay, this angle what you are looking for actually. Okay. I'm sorry, this angle what you are looking for. This angle is nothing but phi 0 minus phi t. So, this angle has to be I mean satisfied here basically. Okay. Anyway, so this is the part what you are looking for. More on that you can see Jarkon's book and all that actually. There is a I mean very neat book, a very popular book actually all over the world, which is fundamentals of tactical and strategic missile guidance and all actually. So, if you take that you will see some of the details of this pre-flight equation, heat equation, all that. There are papers by Eddie Whelan and all a long time, as I told, around 1950s and all, which is where these equations are derived first. Anyway, we will go back to our system dynamics, and then this is our objective. So, this will essentially give us this output that we require. At when the vehicle goes here, my output, which is my location variable, let us say, has to satisfy this equation actually. That is all I will say. So, we talk about this gives us the system dynamics, and then this gives this heat equation gives us this output equation actually. Okay. So, once you have a system discretized system dynamics and there is a discretized output equation, we are ready to apply MPSP actually in a way. We have done that, and then these are some of the other things that is coming into picture. Okay, the discretization of the state equation for control computation, we used the Euler method. Okay, however, for the state prediction part of it, we have used RK4 method actually. Okay. Remember, you have to predict, there is a prediction correction sort of mechanism. You have to see the previous control history, predict where you are going, see the error and then correct the control history actually. So, the prediction part you use RK4 and the correction part you have to operate with some math algebra and all. So, there you have used this Euler method and all that actually. So, the algebra becomes simpler actually. Okay, so then the step size we taken 100 milliseconds, typically this around that figure actually in reality. And then guidance loop closure happens after 1 second of burnout time actually. Okay. And remember, we need a bunch of derivatives, they were all computed symbolically, and iteration folding has also been implemented, but without that also results are alright actually. So, these are some of the results. So, you can see that various range actually. Okay. For various ranges, if you even start with same initial condition, the algorithm takes care and ultimately gives you this control history. It adjusts the control history in such a way that no matter where you want the target, suppose you want this 3500, 4000, 4500, wherever you want, okay, starting from the same initial condition, the control history is all happening here in this segment only. Okay. After that, this part is a free flight trajectory sort of thing. Okay. So, the point here is it is working and working very well rather actually. And these are the corresponding thrust time curve that is also there. But also remember, this is let us say suppose the middle part is what was prescribed to us. However, in reality it can happen both downwards with larger burning time or upwards with smaller burning time actually. Okay, for these things we can actually, there is a need for online thrust readjustment depending on the motor performance actually. Okay. That details I will skip here, but essentially the idea here is as you start flying you will see whether you are actually underperforming this way. Okay, the thrust that is expected is actually coming out to be lower, or it is overperforming, that the thrust is coming out to be higher actually. Okay, if it comes out to be higher, it will burn out faster. If it comes out to be lower, it will burn slow and hence it will burn out later actually. Okay. So, the fundamental idea here is no matter what it does, the area under the curve remains same. That means, if I really know this trajectory, this baseline trajectory and also the area under the curve, which is obvious anyway, and then depending on the performance of the motor online, I can actually redefine this trajectory thrust time curve, and this redefined thrust time has to be used for computing your guidance command, and hence you really what you need is an online algorithm where you can implement this actually. Okay. So, this is what it is, and also just a small comment, the realistic solid motors and all will behave in a very different shape. They call something called M curve and all that, but here the experiments are not done with respect to those. These are the thrust time curves generated artificially from some sort of a vehicle sizing study and things like that, from very first fundamental principle using the textbook analysis sort of thing actually. Okay. So, like that way. Anyway, the point here is not only it meets various target conditions, but it also meets the same target with whether the vehicle is underperforming or vehicle motor is underperforming or overperforming. If you start with the same initial condition, aim for the same target, but whether the motor is not performing as per the predicted nominal condition, but either it over predicts or under predicts, then the thrust time curve is readjusted online, and hence wherever you start readjusting, there will be a different trajectory actually, okay, from there. And then the point here is the online algorithm happens to work invariably actually. Then how about computational time? That is what we have been claimed, that this method is computationally quite efficient and all. So, obviously, there is a necessity of computational time as well, but this is typically done in a different platform. There are real time computers available, and then algorithms needs to be coded, and it has to be evaluated properly, and it has to be further evaluated in this online this onboard computer platform and all that. We have not done anything of that. We have simply taken the same PC that you have used and tried to kind of evaluate how much time it takes actually. Okay, and this is evaluated in the Pentium 4, slightly older version of the computer with 512 MB RAM, and programming happens to be the MATLAB 7 platform. The first control update, which is the longest one, it talks about it takes about 1.75 seconds actually. So, typically a code written in a low level language will require much lesser computational time, and if your code is optimized also and it runs only that thing, nothing else, then obviously the real time issues can be evaluated properly. But however, you can think that okay, it can operate safely about 1:100 ratio sort of thing actually. Okay, or maybe sometimes people tell it is 1:200 ratio rather actually. Remember, MATLAB is a line interpreter. This is compared to that, the code will actually generate a compiled code and then try to run fast actually that way. Okay. So the point here is this 1.7 seconds. Remember, this is not minutes or hours; it's seconds actually. So within 2 seconds, you are able to get a control history update actually. Okay, in MATLAB platform. Okay, and then where the background processes are also running actually. Okay. So in that sense, I think people do agree that it in an online implementation, it is possible to do actually. Now, what about this performance, the cost function performance with respect to, so let us say something like a true optimal control formulation, because MPSP is ideally speaking cannot be called an optimal method, but rather some people try to kind of emphasize that it has to be called a suboptimal approach actually. There are reasons for that again, and one of that happens to be because we are stopping because we are actually bothered about output convergence. We are not waiting until cost function converges and all that actually. But how about looking at this actually? Suppose the output has converged, then where does the cost function lead to? It may be a slightly different control history per se. Okay. However, the cost function sense is essentially leads to almost the same value. Okay. Because there is some energy loss here, I mean area loss here, area gain here, and things like that way. Okay. Or probably you can think about this is the NLP solution, the blue one is the benchmark one, let us say. And this is solved from direct transcription, which this is using NLP approach and all, which I will discuss in some of the lectures later basically. Essentially, it actually tries to solve the full optimal control problem as it is actually that way. So, compared to that, this particular method that you are talking about, well, this has to be, it is not MPC, it has to be MPSP basically. Okay. So, this part is MPSP and this part is NLP, which is transcription method sort of thing actually. Alright, so this is the closeness that you are looking at. Okay. So what message is the MPSP actually leads to very close to optimal control solution actually. Then there are issues, the problem does not stop there. There are issues like, okay, you have assumed that the thrust time curve, the area of the thrust time curve remains constant, but it so happens that it need not be accurately known basically. That means there may be uncertainty on that value itself basically. So whatever scaling you are doing, or even the nominal profile that you are using is actually incorrect, because the energy content may be different actually. Okay, so in that sense, you actually extended the work a little bit further. I am not going to talk you too much on that, because that is out of this optimal control domain sort of thing. But the whole idea is we first assume that up to 90% it is actually 90% of the predicted energy is actually available without fail. Okay, so up to that we will design an MPSP guidance, and then for the remaining part we will switch over to this dynamic inversion based guidance, details of which you can find it in our references and all that, which will actually ensure, see, this MPSP guidance will ensure that the error goes to 0. But what is more important is error should stay at 0 also basically. Okay. So essentially the whole problem here boils down to, because the error function can cut the point several things actually. So this is error and this is 0 value. So there are several places it can cut. Now if it is a liquid engine, you can stop anywhere and the job is done. But if it is solid engine, it has to cut where the burnout point actually. It has to cut at TBO only. That is the major restriction. What happening in addition to that, what happens here is what you are talking here is error value should wherever this is positive or negative either way, wherever it starts, it should go to 0. But going to 0 is not sufficient. It has to stay at 0 at a finite segment actually. Okay. Now if it stays at 0, then anytime the thrust burnout happens in this segment. Okay, what you are looking for, okay, in this segment happens to be energy insensitive. That means the error is still 0 anyway basically. Okay, so going to 0 part, this is the first part, that is this part is ensured by MPSP, but staying at 0 is ensured by dynamic inversion. And also remember, there was a necessity that if you aim something like that, then you also aim that while going to 0, the derivative should be also close to 0. The derivative, in other words, the approach should be like the way I have shown you actually. If the approach is somewhat like this, let us say, then you are talking about an infinite slope here and then suddenly correcting to 0, there will be control discontinuity, and any discontinuity at the end is extremely difficult to track, you just can't do it actually. So, this is not an option basically. So, what you really need, okay, sorry, what you really need is something like this kind of a thing, okay. Oh, sorry. Where the error should not only go to 0, but it should stay at 0. While going to 0, the derivative should also approach towards 0 actually. So, then maintaining becomes easier actually. Okay, so that thing has been done a little bit. I am not going to talk too much on that, but essentially it has been done, it is assured, and the whole idea here is it actually kind of eliminates this so called VTP requirement, is a velocity trimming package they call. So, what it does is even though you talk about a solid motor, then along with your warhead you essentially take a small liquid engine and then derive the benefit that the liquid engine can be manipulated, liquid engine can be used to cut off the thrust anytime you want actually. And because it is sitting on the along with the warhead, the correction can be done anytime along the path actually. Remember this, going back to this thing. Imagine a situation where there is a there is a warhead, the warhead keeps on going here. So, along with the warhead there is a small liquid engine. So, any amount of inaccuracy that you see somewhere, it can be corrected any point during the free flight actually. Okay, the entire free flight is available to you. Okay. So, again this is done in the initial phase as much as possible, because that is where the sensitivity is high and hence the control effectiveness is high. So, very close between this point 1 or point to the this maximum height point. Okay, within that the solution, the correction is typically applied actually in general. Okay. Anyway, so that is the velocity trimming package they call. There is a small liquid engine which goes along with the warhead. But the problem with that is anything that you have along with the warhead, there are two things. One is it eats out the space and it also adds to payload weight. And means what you are doing is actually you are talking about something like a compromise in warhead size, or you are talking about compromising something like the range actually. Okay. So, the whole idea is can you really eliminate VTP or at least minimize that requirement to a very great value basically. So, that is what we claim that it probably can be done. With looking at the results, it turns out to be slightly more promising actually. The result part, you can see all the results not only they are going to 0, but they are actually staying at 0 towards the end. That means, any time that the burnout can happen, but still your error will continue to be 0, and hence all of that will be target intercepting actually. Alright, so this is what it is actually. And then again computational time point of view, this time it was some sort of a similar platform and all. We also use fast control update is actually 0.47 seconds. It happens to be quite smaller than the other one also basically. Okay. So, the conclusion of this particular problem, it talks about the algorithm successfully works and tested for various ranges. It leads to high accuracy, and remember accuracy in the sense of plus or minus meters actually is nothing. What you are looking for is, even if the accuracy happens to be of the order of 2-3 kilometers, it is very much okay. But what you are talking here is strategic warhead sort of thing, which is the wide area kind of restriction basically. So, having plus or minus 1 meter is extremely good actually. It's the hard constraint. This happens because the final constraint is put as a hard constraint actually. Also observe that it is computationally quite efficient, and hence it is a possibility of implementing it online in future actually. Okay. Also, we have done comparison studies with NLP solution which actually slows some sort of very close match actually. So, this is about the ballistic missile problem. Then there are energy insensitivity of guidance design extension of that using this dynamic inversion along with MPSP. Essentially meets the specification. It takes about some sort of robust guidance algorithm. Okay. So, it's essentially it makes it kind of energy insensitive in a limited sense actually, at least. Okay. Alright, what next? So, I told it does not necessarily act on only a strategic thing, the conventional guidance also it works. So, let us quickly go through that kind of idea. So, here I am talking about some missile guidance problem with impact angle constraint as well. So, what you mean is not only you have to hit the target, a conventional target of course with very good accuracy, but at the time of hitting the target, it also there should be some angle constraint for the velocity vector, and there are reasons for that also, which I will summarize here. So, why angle constraint? The very first thing that you can see is enhancement of warhead lethality. That means there are certain targets for which there are vulnerable parts, either front or top and things like that. So, if you talk about that kind of target, then your enhancement of the warhead lethality happens only when you attack from the front actually, okay, or attack from the top like that actually. Okay. So, that is one reason why you want to put angle constraint guidance. Okay. And there are some certain things like well, I will retrace a little bit here. There is something called enhancement of warhead lethality. In other words, if you approach the target in a particular direction, at least in the velocity vector sense and all, okay, the essentially the if once you explode your own warhead, then the damage on the target will be more actually. Okay. So, for example, there is front attack and all that. The target is coming there. Okay. Target is coming something like that. If you go in a front attack mode and then explode it, there is a very large chance that you will capture the target actually. Okay. But if you go some other direction, then suppose you attack it, I mean some from this direction, let us say, with other mission objectives, but it will explode this way. But by the time the fragments cross this, the target should be somewhere here. If it is here or here, it has already crossed or is about to cross before crossing, then it is virtually useless actually. So that is what the warhead lethality is all about actually. Okay. 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 Now, coming to that, there are certain vulnerable parts, or you want to attack the weak location of the target. For example, top attacks for tanks. So, the tank there is a manhole for the so that the driver can enter the tank, and hence there are some weak parts in the tank. It is not actually armored heavily from the top, whereas it is armored heavily with the thick metal sheets and all that from the side and all that actually. So, if you really want to attack a tank, then better do that in a stop attack sense actually. Okay. And there are certain mission demands, for example, bunker busters and terrorist hideouts in urban areas and like that. There where you again want to go in a particular direction only, either to minimize collateral damage or to minimize the mission itself demands that actually. If a bunker buster means there are certain layers of concrete that you have to explore, go deeper and deeper and things like that. So, unless the velocity vector is perpendicular to the surface, the vehicle may escape and go inside the earth, and it does not serve any purpose actually. So, then similarly, if you have these terrorist hideouts in urban areas, there will be multiple buildings and all. Unless you come from the top or in a particular direction sense, you will your other structures and all may come on the way actually. So, it will not do the job basically. So, the mission itself demands that you go in a specific direction sort of thing. Then there are ideas like coordinated attack by multiple munitions. That means, if you have 3-4 things, let us say small UAVs and all, and they have to go and attack from a particular direction only, then only combined effects will be maximum actually. If individually they attack in a different sense, different location, different direction and all that, the combined effect may not be much. But if all of them go to the same location in the same direction sort of thing, then the effectiveness is much more actually. Now, people talk about not only the same location and same angle, but they also talk about same time actually. That means 4 or 5 UAVs will be there, they will all go at the same time, same location, same angle of the target actually. The effectiveness will be much higher basically that way. Then there are also reasons for something like countermeasures for enhanced stealthiness. For example, if your radar is looking in some particular direction, you want to, the enemy radar is looking in certain particular direction, you do not want to go in that direction and then make yourself visible to enemy. So, if you go in the backward direction sense in all that, so for them, in those situations, you can think of it as something like a countermeasure actually. Okay. So, it has done for enhanced stealthiness. So, you can introduce these countermeasures actually. You can also think about range enhancement. It is typically not a range enhancement formulation, but it happens indirectly, because if you happen to something like, let us say, a top attack, then you have to actually top attack of a target which is of the same altitude or above you basically, let us say. Then what happens, the vehicle, the missile has to climb even further. That means the atmosphere density comes down by flying at the high altitude, and once the atmosphere density is down, the drag is less, and if the drag is less, the range can be more actually. Okay. So, this is what is the range enhancement indirectly sort of thing. then sometimes it is done to increase the observability of the target also. That means you purposefully take a maneuver sidewise and all that, so that you can see the target better actually. So that's another reason why you want to have this angle constraint gradient and all. So there are several reasons. I have listed out only about 6-7. There are some of the reasons also for which we really need this angle constraint gradients actually. Now, existing methods of 3D gradients. Okay, this particular thing we are interested in talking about gradients in 3D sense, and then angle constraint will happen in 2 angle sense actually. So, what is the motivation for that? Okay, the 3D PN and augmented PN laws available. Okay, but I mean there are couple, not too many. There are a couple of them are available. However, very less of them will actually talk about 3D impact angle constraints. Okay, angle constraint will be discussed. If you see the literature, most of them will talk about 2D only. Actually. But here our aim was to kind of experiment in 3D domain. Okay. And then existing solutions which are already there, okay, they are either non-optimal or based on kinematic only. Now, we want to extend it further, we want to talk about the full nonlinear dynamic point mass equations actually, and then using those equations you want to design gradients laws actually. Okay. And okay, so the challenges, first thing is the strong nonlinear coupling between the elevation angle and azimuth angle basically. That should be accounted for. What you really need is 0 or near 0 misdistances. Remember, unless there is a 0 misdistance sort of thing, most of the angle constraints are meaningless actually. In other words, if you only when you hit the target, then only angle becomes much more important actually. Yeah. Otherwise, it is there, but it is not that much important actually in a way. Yeah. Alright, so as I told, 2 angle constraints at the same time has to be ensured, that is called 3D angle constraint. And then lattice demand has to be minimum on the way also. Lateral acceleration demand has to be as minimum as possible on the way actually. So, what is the problem objective now? The problem objective is to design a 3D optimal gradients law for maneuvering, moving or stationary targets on the ground with thrust port, with autopilot delay or without thrust ports. Either you can simply release a vehicle from the aircraft and it will go there. It can also have its own thrust ports, I mean depending on the mission of course actually. So, this is the type of thing what you are looking at. You want to release a vehicle from air, let us say, and there is a target, ground moving target actually. It can be stationary, it can go in a constant direction, it can take some maneuvering path, whatever, maybe the road condition is like that, or it takes intensive maneuvers, intentional maneuvers just to evade the target, or just to evade the attacking missile, something like that actually. So, it can be either stationary or moving in a constant direction or moving in some sort of a time varying acceleration actually. Okay, so not only the vehicle has to be guided, or the missile has to be guided in such a way that ultimately it should not only fall on the target, but the velocity vector should also give rise to this desired I mean flight path angle gamma mf and desired psi mf both together actually. Okay, so this is the problem that you are looking at actually here. The dynamics missile model and target model are typically done that way. Remember, even though instruments are available for extracting target information, it cannot be full information per se. So, typically target models are done in kinematic sense. Wherever the missile model, you have it is a sensor system, and not only that, the sensors information can be extracted for the autopilot actually. So, that means the sensor information is more detailed as far as our own vehicle is concerned, and hence detailed model can be used for the missile. Target is simplified kind of kinematic model basically. The state equations are like that, control is like that. Again, there was a necessity of this normalization and all. So, we have done this normalization. Okay. And as I told, the target acceleration can be either 0, that means just a straight line movement. It can be constant AYT, that means some sort of a constant turning, and it can have also this waving sort of sinusoidal thing, periodic maneuvers actually. So, let it be anything, still the algorithm has to work actually. And also remember they can change actually, that means target can start with straight line movement, on the way it can change its strategy to constant or maybe sinusoidal or combination of that actually. But what you are assuming here, the information is known to us actually. What the target is doing is actually extracted from an estimation algorithm on board, but that part you are neglecting here. You are assuming that okay, that part is done separately and it is the necessary information is available here actually. Alright, so these are the normalized dynamics and all. So substitute that. These are the discrete state equation and all using same Euler integration and all that, and then these are some of the results actually. Okay, you can see that we have put only a single angle constraint here. Okay, what you see here. Okay, this is what the Pn gives. Okay, but this is what we want. Okay, and there is an angle constraint here. It has to be some sort of vertical here. So it happens to be like that. And these dotted lines are the projection curves actually on these two 2D planes. One happens to be in the xy plane, this is the one, and then happens to be in the xz plane actually. And from xz plane you can see the angle is 90 here, okay, and there is no angle constraint in the xy plane, so it is free anyway actually. You can also see there are the comparison with respect to this lateral oscillation studies and all that. So, see this is 1 and 3rd happens to be the same AZ, one coming from MPSP, other coming from PN, and then 2 and 4 are also similar. So, if you see 1 and 3rd, okay, you can also see that the 1 is much more smoother than what is happening is 3rd, and the maximum value also happens to be low. This happens to be maximum value is something like 3.5 around, but here the maximum value is around 5 actually. Okay, so it is smoother, it is I mean magnitude wise also there is a lot of advantage actually. The similar advantage happens to be the other case as well actually. If you compare these two, this line happens to be much more smoother actually, yeah. Okay, and the maximum value also happens to be lower. Anyway, so this is what it is. Then what about two angles now? Giving I mean two desired angles and all that, you can still do that. The formulation allows that. So, there are various combinations of 3 different cases we have shown with different desired angles and all that actually. You start with the same initial condition, but suppose your desired angles are different, then what happens actually? You can very clearly see that no matter what you desire, the algorithm is able to find out. And again I emphasize here, it is not extensive tuning which is typically done in industry and all that. Case by case, depending on situation and things like that. There are variations of PN gradient law which will actually try to kind of give you some angles and all that. So, people can attempt doing that, but it requires heavy amount of tuning, scheduling and all sort of thing. This is absolutely not needed here. You just code these numbers, whatever numbers you can feed it to the algorithm just before launch, and then it will take you there actually. So, then this is a different one. So, we start with 3 different initial conditions, but as ultimately aim to the same condition actually, same position and same angles also basically. So, this is what is also again happening there. Okay, the lateral oscillation advantages as well actually. Another plot, there is something called zero effort miss. I mean the details you can see in a missile guidance book. And the zero effort is okay, from wherever I am, from there onwards, if I go with zero effort, that means lift is 0 actually from there onwards, then what happens actually? And you can see that the solid line happens to be MPSP, which is much more less oscillatory, okay, much more smoother and less oscillatory, and hence there are a lot of additional advantages as well actually. Coming to another class of problem, this is a different class of problem. This incoming things is actually a ballistic missile. You want to defend it before it destroys you and all that actually. In those settings also you have experimented this logic. There is a different class of challenges again here. There is a very high speed target and hence very less engagement time, very high line of sight rate, and ultimately what you really require is zero miss distance rather. And there also has to be some impact angle constraint. Directional warhead is also a necessity, but latex saturation has to be accounted for. But due to less dynamic pressure, you want to engage the target in high altitude actually. So, high altitude means less dynamic pressure, and the latex saturation is a constraint there actually. So, here what you have done is you extended the logic of this loop design and all. You can think of taking out the loop. Okay, this is what the conventional 3 loop thing, and what you have done is we have taken out this, okay, the outer loop sort of thing, and this essentially leads to this so called this partial integrated guidance and control design sort of thing. Okay, so this is what it is, and this I mean there are advantages and all. I will encourage that you read this references and all that actually. I will not take you through that, but essentially there is outer loop and there is inner loop. Outer loop operates on MPSP, inner loop operates on dynamic inversion actually. So, there is also application there. There are papers available also to read. So, in summary, in conclusion, MPSP technique is a very promising technique for optimal missile guidance in general. Okay, and essentially the various challenging problems you have solved, and I also encourage all of you to kind of put your hands on various different problems. I am very sure you will be surprised to see the results in a very good way actually. Alright, so there are extensions available for MPSP. As I told in the previous lecture, we have proposed this MPSC techniques, and there are other techniques as well, generalized MPSP and all. I will talk about those in next class. And as I told, this technique has found worldwide acceptance slowly actually. Okay. Some of the references about missile guidance, the classical this air to ground missiles and all that, the impact angle constant problem. You can see that in this particular reference is already published, and there is another application which talks about this mid course guidance sort of thing with alignment angle constant, very close to the impact angle constant sort of problem, but a different class of requirement sort of thing. You can see that also in this journal paper actually. Okay. And this is another journal paper which talks about energy insensitive guidance of the ballistic missile sort of thing. Also available, you can see details out there. And this is the first paper which from which I have discussed the previous lecture as well, which talks about this the very basic paper which talks about the very first idea. Okay, available here. Alright, so with that I will stop here this lecture. Thanks a lot.